Here I've got a little demo set up where I've got this string stretched between this machine and down here it goes over this rod, and I have some weight hanging on the end of it, so there's a certain amount of tension that's put in here. So this device is designed to go up and down at varying frequencies, and this machine right here is designed to create those frequencies. So for example, I don't know if you can read this on here, but that says 1.1 on the screen, which means this is going up 1.1 times every second. That's the frequency. And if I turn it up, that's 2.4 times per second. So what it's doing is it's raising this up and down real fast, sending waves down this string, which are bouncing off the other end and coming back. Now let me just show you something. If I increase the frequency, I get to a certain value. This is 12.2 hertz, 12.2 cycles per second. So that's going up and down 12.2 times per second. And you get this, what's called a standing wave. So remember that frequency, 12.2, because I'm going to keep increasing it. See, now it's not oscillating anymore. Now it's at 24.5. That's almost exactly twice the first frequency. Now let me go up again. This is at 37.1, which is very close to 3 times that first frequency. So there's certain frequencies with which I'm vibrating this string. It'll vibrate at in this sort of what's called a resonant way. It has a fairly large vibration, and because it's vibrating a large amount, it can produce sound waves as it moves through the air of these particular frequencies, and these are the frequencies that it tends to produce. Let me just go up one more. Okay, so you get all these different resonant vibrations that can occur on this string. So I want to talk a little bit about electron orbitals and shells. How is it that the electrons stack up on an atom? Do they orbit an atom, sort of like a planet orbits the sun? Well, that's what people originally thought, maybe 110, 120 years ago. But then they found out it isn't like that. And what actually happens is electrons take on these different shapes. It's a little bit like the different wave modes of standing waves on that string, where if it vibrates at different speeds, it gets more and more complex sort of structure. Well, that's a one-dimensional vibrating thing. An electron is a wave-like particle, and it's a three-dimensional object, and it has these different, more or less, vibrational modes that different forms that it takes when connected to an atom, and the different modes are called orbitals. And they're not orbits, or an orbit is something that goes around like that. But since that's what they originally thought, they call them orbitals because it's a different idea. And to understand a little bit about electron structure, atomic structure, the way atoms bond together into molecules, it helps to have a little sense of these orbitals and how these orbitals collect together into shells of orbitals. So that's what I want to talk about now. So let's say I have a lone carbon nucleus. So that's the little nucleus in a carbon atom. 6 protons, 6 neutrons. And there's no electrons here. So this is just a lone nucleus all by itself. It has positive electric charge, so electrons near it would go into their orbitals, but let's say it's isolated at first by itself. And an electron comes up and is attracted by the positive electric charge. It goes into what's called the lowest energy orbital. This is roughly analogous to the single lobe of that vibrating string. And it simply surrounds the nucleus in a spherical shape. And literally the electron is, all these particles are kind of fuzzy, and at the center of this electron is the nucleus. So this is called the lowest energy orbital, sort of like the lowest energy or the lowest frequency vibration of that string. If another electron comes in, it'll join this one in that lowest orbital. Two electrons can occupy an orbital. So that's two electrons. So now we have what? There's two electrons on this carbon nucleus, but there's 6 protons, so there's still 4 more protons than electrons. So if another electron will come in, it still attracts it. Okay? The next one that comes in goes in the next higher orbital. Usually I'm better drawing circles. But it's another spherical shape. So the analog to the string having 2 standing waves in it is another spherical shape surrounding that atom, but it's bigger, it's larger in size. So the third electron goes into this orbital. So now there's 6 protons and 3 electrons. So it still has a positive charge, it's still going to attract in more electrons. And the fourth electron is going to join the third in that orbital. 2 electrons can be part of one orbital. But what about another electrons? So now we have, what, 4 electrons and 6 protons. There's still room for more electrons. Well, the next orbital is, let me use orange for this one, it has a different shape. Sort of hourglass shape, and it's centered on there. So this is a 3-dimensional, dumbbell or hourglass shaped thing that's centered on the nucleus. So these electrons, this is the electron, right? It has this sort of double-lobed shape, and this is again one of the orbital possible shapes that an electron can take when it is connected to the center of this atom. What about another electron coming in? So let's see, we have 1, 2, 3, 4, 5 electrons. There's still 6 protons, so there can be one more electron that can bond onto this carbon atom. It'll take on an orbital like this. So this may seem odd, but this is really the shapes that electrons take when they're attracted to the nucleus of an atom. Now is when I can show you something about shell structure. These first 2 electrons are in what's called shell number 1. And 2 electrons will fit into that shell. It's composed of 1 orbital all by itself. And 2 electrons can fit into that orbital. These orbitals, this round one and these 2 dumbbell-shaped ones, or 2 hourglass-shaped ones, they're all about the same physical size. They make up shell number 2. And there's one more orbital in that shell number 2. It's another one of these hourglass-shaped things, but going out of the board. So if another electron joins this atom, then it will go into that orbital. These orbitals and this one are about the same physical size, and they're said to make up shell number 2. And all in all, there are 8 electrons can fit into that orbital, because there's this orbital, which can handle 2, this one, 2 more, this one, 2 more, and then the hourglass shape going this way, 2 more. So that's 8 electrons. So shell number 2 can hold 8 electrons. Shell number 3 is similar but bigger, so that also holds 8. Shell number 4 can hold 18. Shell number 5, 18. Number 6 can hold 32, 7, 32. And that's about as many as you ever see in nature, because beyond that there's no bigger atoms. So these shells of orbitals, that is the form that electrons take in atoms. So you can see this is the way electrons stack up in their orbital shells. They always stack up from the inside out, and the bigger the atomic number, the more electrons there are. So for example, nitrogen is atomic number 7, so there's 2 electrons in shell number 1 and 5 in shell number 2. Oxygen is atomic number 8, so there's 2 electrons in the inner shell and 6 in the shell number 2. And what you're going to do in the exercise, you'll print out this worksheet which has all the elements up to, I think, nickel. and all the orbitals are shown there, and you're just going to fill in the number of electrons in each of the shells, and then just take a picture of that and submit those pictures. There should be 2 sheets because it goes all the way up to, I think it's atomic number 27, which is nickel. By the way, when you look at these shells that are in these diagrams, you can see they get progressively smaller. Like shell number 1 starts out large in hydrogen and gets progressively smaller. That's really the way they are in nature. The more protons in the nucleus, the stronger the attractive force, and it actually makes the electrons smaller, makes that shell smaller. So I tried to duplicate this in the real physical size. And one last thing, the outer shell is called the valence shell, V-A-L-E-N-C-E. The valence shell of hydrogen is shell number 1. The valence shell of oxygen is shell number 2. The valence shell of iron is shell number 4. In other words, whatever is the outer shell of the atom, that's called its valence shell. That's important because it's those valence electrons, the electrons in the valence shell, that end up bonding, involved in the bonds with other atoms. So we'll be talking more about valence shells and valence electrons later on. Okay, so that should get you going on the exercise.